No. Well, good morning, and welcome to the presentation, Do Certain Types of Developers or Teams Write More Secure Code? The subtitle of this presentation is Human Factors in Application Security, and the reason for that subtitle will become obvious in a few minutes. First, let me introduce myself. My name is Anita Damico, and I am the CEO of CodeDX. I'm also the director of Secure Decisions. Secure Decisions is a cybersecurity research organization that does work primarily for the U.S. government. We do cybersecurity research and develop new technologies. And then those technologies in application security, which are the most promising, we bring over to CodeDX, which is a separate company that was spun out of Secure Decisions, and we mature those AppSec technologies and commercialize them. I'm here today with Chris Horn from Secure Decisions. He's a senior researcher there, and some of you may have seen him present yesterday on the topic of doing research in benchmarking static code analyzers. So he'll be doing part of this talk today. So there are 4 parts to this talk. Part 1 is going to talk about why it is that we do research in human factors that affect code quality and security. Part 2 we'll discuss how we do that research. Part 3 is the crux of this presentation, and it shows you some of the results of what we have found to date. And then part 4 is where can we borrow some lessons learned from other non-software domains about human factors that affect performance. So, ready to go? So let's talk about why. Why should we be investigating human factors that affect code quality and code security? Well, software vulnerabilities are the gateway to most major breaches. In fact, the Verizon Data Breach Report showed that more than 90% of breaches in the information industry started with using web applications as the attack vector. So we know that we have to find these software vulnerabilities, yet it still takes a really long time, despite the state of the art. The Heartbleed vulnerability took about 2 years to discover. The Apache Struts vulnerability took about, that was used in the Equifax breach, took about 4 years to discover. And academicians have studied open source repositories and found that despite the fact that there are many eyes on the code, most vulnerabilities on average take 2 years to discover. Now, actually, it's 2 years to be reported. They very well may be discovered long before that, but they aren't publicized for 2 years until after they were originally introduced. So that's a long time for a vulnerability to sit there and remain unknown to most of the users of the open source software. Now, there are ways, of course, of finding security weaknesses and vulnerabilities. Most people here are familiar with static application security testing tools, SAST tools, that can find security weaknesses, which may be indicative of vulnerabilities. But there have been benchmarking tests of SAST tools done by the U.S. government, done by the National Institute for Standards and Technology and NSA. And they took test suites of software with known vulnerabilities and ran commercial and open source static analyzers against them and found that on average they found 14% of the known vulnerabilities. And that each tool found almost a unique, different 14%. So you need to combine the results to get good vulnerability coverage. This is why a lot of people still rely on manual code reviews. And the problem with manual code reviews is that there's a lot of software to go through. Where do you orient yourself as to where to look? So that's where human factors comes in. What if you were looking for vulnerabilities in code, suppose you were hunting for them, perhaps you could search on who the developer was or the developer characteristics. Or maybe you know something about the team and you know that there's something about the team characteristics that is more likely to introduce security weaknesses. Or maybe when the code was written, time of day, even time of year, or where the code was written. If you could use that to hunt for vulnerabilities, then you would have an advantage in where to start looking. So these factors that I described are called human factors. Human factors are properties of people and their environment that affect human performance. So there are a number of types. There is psychological. So, for example, an individual's ability to focus their attention is a human factor, or their memory or the way they make decisions. On a group level, there are human factors such as the way people collaborate with each other or the way they communicate with each other. There's also cultural norms that will affect the way people perform their job as a group. There's also physiological factors. For example, is the individual fatigued? This could affect their performance. Or circadian rhythm. A little bit about circadian rhythm. Circadian rhythm is the changes, the diurnal cycles that your body goes through during the course of a day. So there are certain chemicals that are associated with your alertness and arousal level, and those chemicals shift during the course of the day. And it's known that circadian rhythm affects things like the attention of watchstanding officers on the bridge of a ship. So maybe that's relevant to software developers. And then finally, environment. So if the environment is noisy, if it's distracting, if there are temperature changes or lighting, these are human factors. Now, these human factors are considered in almost all safety critical systems in their design and also in the analysis of failures. So why not look at them in software engineering? So that's what we're doing. We're looking at human factors in software engineering to see if we can find correlations between certain human factors and the resulting quality of the code, the quality and the security of the code that software developers are producing. And I'll describe a little bit about how this research is done. So the way most of this research is done to date is, first of all, it's done by mostly academia. So one example is Rochester Institute of Technology. That's their logo up there. And what they typically do is they work with only open source projects, fairly medium to large size repos like Linux kernel or Chromium, Apache, Postgres, Tomcat. And they mine those repositories for what they consider indicators of human factors. Now, they can't actually measure somebody's fatigue level, but they might look at what the local time zone was that when the code was committed. And if it's 11 o'clock at night, they might infer that the person may be tired. Similarly, they can't look at the actual size of a team, in terms of the team dynamics, but they might look at the number of developers who contribute to a file, or look at the comments on the commits to see how people are communicating with each other. So they're looking at indirect indicators of human factors. And then they look at the publicly disclosed vulnerabilities in the open source. And they basically make two piles of results. They take, let's say, Apache server. They'll say, here are all the files that have vulnerabilities in them, that have at least one vulnerability. And over here are all the files that have no vulnerabilities. So they have two piles. And then what they do is they try to maximally discriminate between those two. What are the unique characteristics of this pile that have vulnerabilities versus this pile over here that doesn't? And they start making inferences based on that. Now, the other type of study, and there are very few of these, are done in proprietary environments. And it may be that the way you develop in a proprietary environment is different than contributing to open source. So there's studies by Microsoft and ATT and Nortel. Microsoft has a human factors group that studies these types of things, and I'll be referencing one of their published papers. What we are doing is we are now under contract to the Defense Advanced Research Projects Agency, DARPA. It's a U.S. government R&D organization. They have a $3 billion a year budget, and they did invent the internet. It's called ARPANET after DARPA. It was called ARPA at the time. And so what they've asked us to do is expand on this body of research to start looking at proprietary environments and also to study human factors more directly. So let me tell you a little bit about how that work is going to be done and is being done. So there are three different types of approaches that we're taking. What I'm going to be talking about today is mostly this first approach, was a retrospective analysis. That basically means a historical analysis of existing software repositories, issue trackers, basically resources. And we're looking at both open source as well as proprietary code repositories. And when we do that, we look for these human factors indicators in the repositories, and then we correlate those to measures of security. Now, if it's an open source repository, we can use publicly disclosed vulnerabilities. But for both open source and for proprietary code bases, we're also using the results of static code analyzers. So basically SAST findings. Those are indicators of both code quality as well as code security. And the advantage of using them is that you can apply it both to open source and proprietary code bases so you can compare. Also, since we know that vulnerabilities remain unreported in open source for on average 2 years, these weaknesses that are found in the SAST tools may be indicators of problems even if a vulnerability has not been disclosed. Now, the other thing that we do with these proprietary code bases is that we're not just looking at the code repositories, but we'll work with an organization and see what other kind of data they have. Do they have information about the level of experience of the developers or their education? In one case, we have time card information, and that tells us how many hours the developer worked that week, and we can correlate excessive work hours to code quality or security. It also tells us on the time cards how many different tasks they build. So are they focused on one thing all day long, or are they constantly context switching between different tasks? Now, the second type of analysis that we're doing is concurrent analysis. And that is where we study developers as they code. And we started this part of the research program already, although I don't have results to report. I hope to report it next year. So what the concurrent analysis does is we instrument the developer's environment, and we measure various human factors directly. So they sign on in the morning, and we say, good morning, how many hours of sleep did you get last night? And during the course of the day, 2 other times, we ask them about their subjective fatigue level. We also ask about interruptions, what they're listening to on their earphones, and how much communication they've had with other members of the team. Oh, you've answered already? Okay, or I did. Okay, so then third type of approach is vulnerability history analysis. This is also fairly new. We're taking vulnerabilities that have been disclosed in open source, and we know that it was discovered over here in time, and over here in time, and we go back in time to see when was it originated? What was the originating commit that caused that vulnerability? And what we're doing is we're looking at what were the factors in play in that repository at the time. Were there a whole bunch of people introducing new features? Were there a lot of people a lot of more people? Was there only one person in the repo? We're trying to figure out what are the indicators of what might be, what are indicators of a vulnerability being introduced. We also go to the time of the discovery to see if we can determine what are the factors in play that help facilitate the discovery of a vulnerability. So we'll hopefully have results of that next year as well. So what we're trying to do is answer the question, can human factors predict code quality and security? And today, we're going to be telling you some of the results of not only our research, but other research that's been done by academia as well as by large companies. So the predictors, here's a list of the predictors. These are various human factors that we'll talk about today. And they are we're trying to correlate those with outcome measures. And those outcome measures could be known vulnerabilities, they could be security, quality, and security weaknesses in the code, could be bug frequency, failure rate. So this is what we're trying to do, predictors and outcomes. So what did we find? A dramatic pause. So let's start with a question. Does code quality vary with team location? In other words, is there a difference between teams that are co-located, and teams that are remotely distributed. So Microsoft studied this specifically, and they looked at the post-release failure rates in Windows Vista and Office. And what do you think? Do you think that co-location versus distributed teams makes a difference, or no difference? The answer is no. Counterintuitively, the answer is no. They looked at all different types of distributed teams. They looked at teams that were in the same building, teams that were in different buildings but shared the same cafeteria, teams in the same campus, in the same region. They looked at teams that were across continents. There was no difference. There was a difference, though, that explained the different failure rates. And it wasn't location. And I'll tell you about that in a few minutes. So you can't leave. Right? How about time of day? All right. This is something of particular interest to me because actually my doctoral dissertation was on circadian rhythm and time of day and sleep deprivation. And so I was very interested in this. And our own research results are not yet final, but I could tell you that there is other research that indicates that late night commits have more bugs than morning commits. Now, why is that? Well, I have one theory, and it's just a theory, and it has to do with circadian rhythm. Take a look at that chart. You may all relate to that. There is a human condition, circadian rhythm, it's fairly universal, that says that there are certain chemicals in your body that increase starting at about 7 in the morning. They increase fairly significantly until about noon. About 2 p.m., they drop. That is your siesta time, right? A lot of you get tired around 2 o'clock. That's why, because there are changes in your body chemistry. They then go back up at about 3, and they stay up, and so you stay alert until about 9 o'clock, 10 o'clock at night, at which point they start dropping precipitously. And you can go into aviation accidents and accidents at sea, and you could look at all kinds of accidents, and you will see far more of them at those times when you have a circadian trough. And so that may explain this. I'll take one question I want to make sure we have enough time, but if you want to.
Well, that just presumes that everyone has the same circadian clock, and we don't.
We do. We're very, very similar. It's very similar.
There were tests, blind tests where people were in a cave.
That's different. That's when you're in a cave. When you're in a cave, you have no sunlight. And so your body doesn't have the feedback mechanism. And the actual normal cycle of a human body is 25 hours, not 24. So if you're put into a cave and you think that you've counted the days, by the time you get to the 25th day, you actually, you had an extra day in there, right? Do people synchronize? Yes. Yes, they are. Mm-hmm. By and large, which is why it's so difficult for night workers to adjust. There are some people who can actually change their circadian rhythms, but they are in the minority. That's more personality driven, but you're still going to, if you measure the urine catecholamines, you're going to see that these cycles are fairly universal. I just want to hold those questions because I want to make sure that Chris it gets time. So, okay, remember I talked about indicators of human factors. So when you're looking at a software repository, you can't actually measure somebody's attention. But what we can do is infer it. And so there's something that we use in this line of research called unfocused contribution. And it is an indicator of how much attention developers are focusing on specific files. So unfocused contribution goes up when developers who are working on a file are also busy modifying other files. They're working here, they're working here, they're working here, or a file has a lot of high unfocused contribution when many developers are modifying it. So basically, a file has a high unfocused contribution when it's not getting the direct attention of just a few developers. So, you think it makes a difference? It does. Yep. The more unfocused contribution, the more insecure the code. So we looked at Chromium and Apache web server files, and remember those piles, the pile with the vulnerabilities and the pile without the vulnerabilities? Well, the pile with the vulnerabilities had a lot more unfocused contribution. Now, we also looked at static analysis findings, and we did this across 4 repos, 2 open source and 2 proprietary. And we found that there is a correlation, a significant correlation, such that as unfocused contribution goes up, so too do the number of static analysis findings in both code quality and security. Number of developers. A lot of people say many eyes make good security. So we measure number of developers by the number of developers that contributed to a file based on the commit data. Think it makes a difference? Yep, it sure does. Remember that Microsoft study that I said there was one factor that was directly related to the failure rates? It was number of developers. It didn't matter whether you were in 2 entirely different contents. If the team was smaller, they had fewer failure rates. If the team was bigger, they had more failure rates. Now we're finding this. You know, that's a very good question. I don't know what they did in Microsoft. I could tell you that because of that question, we asked ourselves in our own research the same question. What we are now doing is not just measuring the total number of static analysis findings, we're actually looking at defect density so that we are normalizing for both lines of code and churn. So when we report our results next year, you're going to see density measures. Okay? So the age of the file, I'm not sure what Microsoft did, but we actually, when we did our analyses last year, we did 2 years worth of data. We did 6 months worth of data. Pretty much, there's a lot of findings hold up even when you're only looking at 6 months worth of data. So, age of a file might have a difference, but it's probably lines of code. And if we normalize for lines of code and churn, we should be able to capture age. So let's take a look at what we found, or what others found. Linux. Remember those 2 piles? Those files that had 9 or more developers on them were 16 times more likely to have a vulnerability. What about Chromium? 9 or more developers, 68 times. Apache, web server, 117 times. Right? Now, we also looked at static analysis findings, and we looked at the 4 repositories, and we found that there is a significant correlation. The more developers that are on a project, the more static analysis findings. So, what might be in play here? We don't know, but one idea is something called the bystander effect. And when you have only 3 people in a situation, if something happens, if you see something, you say something, right? When you have a lot more people at play, everybody else thinks that somebody else is taking care of it, right? So that may be, it's a psychological thing that happens, and social psychologists study this, and it's called the bystander effect. So, looks pretty clear cut, but Chris has some alternative evidence.
That's right. Thanks, Anita. So, not all the research agrees. So there's other research that's been done that has not found that correlation. And so this first one here is a study of 4 different open source projects. I forgot which. I think Postgres is in there. And then these 2 proprietary studies of telephone software. So AT&T is a big telephone monopoly in the States. And in both of those cases, they found that quality, which is basically false, right? So that's a little different than security. And bugs, which is this middle one here, did not have a correlation with number of developers. And so one of the things that we think could explain this is that quality and security are likely different, right? And so there's actually some research that's been done to look to see whether quality measures and faults, right, mistakes, crashes, things of that nature are the same as security, and they're similar but different. They don't always overlap. Another one is developer experience. So who here thinks that developer experience relates to quality? Popular opinion. Yep. So, and just one of the things here, so people weren't able to survey developers in this research. So one of the things they do to measure the developer experience is look at how long they've been active in the code base or in the number of commits they have made to a code base, right? And the research as developers gain experience, they actually are looking as they go. So it's not like you lump all of the developers' commits over their entire history, right? So when they have 6 months of experience, you're looking at 6 months, and when it's a year, it's a year. And in fact, they did. So Microsoft found that the components that have these more contributors more minor contributors have more problems. And the minor contributors are basically people who are making relatively small amounts of commits relative to the total commits to a file, right? So if you've got 100 developers contributing to a file and most of those commits are from like 2 or 3 people, right? Everybody else is going to be a minor contributor. Same thing in the study here of Linux and Postgres. I think we've got one more here. So what's that? Yep. Oh. Day job. Yeah, so that's where I'm trying to remember the details of the study now. They looked at the commit patterns. I think they were using time of day here. So you can tell the difference in especially like Linux and Postgres. You can see time and day differences in different people's contributions, right? So some people contribute primarily at night and some people contribute during the day. And so the people who are during the day are more like, IBMers or Google, whose full-time job it is to contribute to the kernel. And that's different than what, people think of as the prototypical open source developer who's working on their spare time, right? And so they actually found that these people whose job it is are actually making more mistakes. And that's interesting to us because that's one of the reasons we want to study both open source and proprietary software, right? Because we think there might be differences in the sort of fault patterns and the human factors that are at play, right? So people who are working on their own time and of their own volition is very different than somebody who's doing it for their job. And there's different social incentive structures in companies as well. So another thing here is the way that developers interact. And so, there are a lot of interpersonal interactions that are not captured by most development systems, right? So your version control system's not keeping track of if you had a meeting that day or who you talked to or who you're slacking with or anything like that. But what we can do is we can see the editing behavior in the files, right? So if we have the same code in the file that's getting modified by one person, then a different person, then a different person, that's something that we call this interactive churn. So churn in general is the idea of in a commit, it's the changes, right? It's basically the change set. So it's the lines of code that have been modified, added, removed, deleted, right? And so the interactive churn is in that commit, those lines of codes that you added, modified, or deleted that were last touched by somebody else. So if you're familiar with the git blame command, that's one of the ways you can figure this out. And so do you think that basically when developers are editing other people's code, do you think that's associated with more problems or not? Yeah. That's right. So what we've seen we saw it in this Chromium browser and the Apache web server. This is the two stacks of files, the ones with vulnerabilities in their history and the ones without. And so we see that there is more interactive churn in files that have a vulnerability, right? Okay, and then this we just thought was interesting. It's not, I don't have any correlation with outcome measures here, but one of the common interaction patterns, so this paper that's cited here, and just for the reference, all these references are in the bottom of our presentation. So if you'd like to go read the original research, ask us, we'll give you a copy. We've got links, citations to all our work. But this researcher actually studied the patterns by which vulnerabilities is it vulnerabilities or bugs? I can't remember. All these papers are different. Bugs get introduced and then how they get fixed. And the most common pattern here is where basically person A fixes it and somebody else comes or introduces a problem and another person comes in and fixes it. And that's one of the most common patterns versus, two people introducing the same thing or the same person fixing their own problem later. Basically takes a second set of eyes to fix things usually. And so this final section of the presentation is where we can draw lessons from non-software domains. So that's all the things that Anita and I just covered are things that have been studied more in the context of software engineering. Here we've got some slides about human factors and how they have been accounted for in other fields, right? And so we're going to look at mostly transportation, medicine, and occupational health and safety. So that's like on the workplace and things like that. And the first one here is fatigue. And so this is one of the most well-known, well-studied causes of human error, right? It's just well known to degrade human performance after about 17 hours of being awake, which is admittedly a pretty long time. Your performance on a number of tasks, and there's a battery of tests that people run, but your performance drops to about the point where you're close to being the legal limit for intoxicated for alcohol in the United States, right? You're basically drunk. And basically these two fields, there's a lot of words here, but in medicine and transportation, the take-home message here is that both of those fields have limited the amount of hours you can work in a day to about 11 hours, right? They don't let you work more than that. It is against the law to drive a truck for more than 11 hours if you're a commercial trucker. If you're a grad student in med school, you're not allowed to work more than 80 hours in a week, which works out to about 11 hours a day. Right? Because after that point, your performance just plummets. And it's correlated with really bad outcomes in medical contexts, which looks like people dying. Also experience, and so what I wanted to do was say here was that, in software engineering, we don't necessarily have caps on how much developers can work, right? But maybe we should be thinking about that. Maybe we should not be, heroizing the long, all-night marathons, right? Maybe that's not such a good idea from a security standpoint. And experience and qualifications. So maybe we need, from a software engineering standpoint, we need to get a lot more serious about looking at the qualifications and certifications of engineers, right? So, professional engineers is a proper title in the States. And, in order to be granted that title, you have to go to a bunch of school. You have to apprentice under somebody who's done something. You then have to take competency exams and you have to maintain continuing education. And it looks very much the same in a lot of sort of regulated environments, right? Like medicine's the same way. Like that, it could have just as well been like, what it takes to become a doctor and even a lawyer to some degree. And in the federal government, there are a lot of job qualifications and requirements. Just to hold the job, you need to have a lot of certifications and accreditation in order to be allowed to perform the job. So maybe we need to be thinking about what is minimum education for software engineering and security. And then this last one, culture. And so if you were on the last session, I think Allison from Screen did a really great job talking about this. But culture actually matters a lot. And so creating a safety or a security culture is often when I talk to a bunch of CISOs in my line of work. I did a study where I talked to a large number of security practitioners, and you find them basically working within their organizations to create what basically are security cultures. And they don't always talk about it in those ways, right? But raising awareness and creating shared values and having everybody on the same page is a culture. And in medical contexts, these types of safety cultures have been linked with the outcomes in the medical field. So the first is an intensive care unit here, and the second is at a hospital in 10 hospitals. So in the first one, they looked across these intensive care units, and they have this survey that's been deemed reliable to measure the safety culture of that ICU. And when you look across all the different ICUs, you can correlate those safety culture scores with patient outcomes, so complications and deaths. And in the hospitals, basically, they did this intervention, took 2 years, but they were able to shift the culture, and that was associated with improved outcomes where the cultures shifted. So cultural change is slow, right? It's not something that happens. It's changing people's opinions and beliefs takes basically at least a year, right? But this is something that we should probably be paying attention to. So with that, I'm going to turn it back to Anita.
Thanks, Chris. Oops. So let's wrap up. We really believe that there is a need for research into the human factors that affect code quality and security. And we are looking for teams, especially proprietary teams that would like to participate in this research. We're looking for code bases, proprietary code bases that we could study. Ideally, if you have information about the developers of the teams or the environment, that would be very helpful. Or if you're interested in working with us, we can work with you to figure out what are the human factors that your organization is interested in. And then we could figure out a way of instrumenting or collecting that data and come up with some actual empirical evidence to determine whether or not those human factors make a difference. And then if we do find differences, what do you do with it? So what we're really trying to do is study things that are actionable. That is that if we find something like number of developers or number of hours worked, that you can actually do something and change the work environment to facilitate a more secure code environment culture. But you also can use this information to look for vulnerabilities in code. So what have we learned today? Where would you start hunting for vulnerabilities based on what I presented? Code committed after midnight. Probably, it very well may be buggy, if not have security weaknesses. Files with unfocused contribution or attention. These are where multiple developers have contributed to many other files. Right? That's basically what it is. Files with 9 or more developers. Files where contributors had little experience in the code base. We sometimes call these drive-by committers. And also files with high levels of interactive churn. So that's our presentation, and we'd be happy to field questions. Richard, I know you have a question.
That was extremely interesting.
Well done, both of you.
Thank you.
One of the areas that I believe strongly in that should be studied and that can make a huge impact, and you touched on it, the culture. You know, what about areas, for example, where mistakes are frowned upon, where creativity is stifled? What about cultures where the application team and the security team aren't interacting and working well together? What about cultures where a company is pushing, get it out, I don't care, right? These things are probably more impactful than any of those, but they're harder to change because it's from the top down. Mm-hmm. And so I'd be curious to I'd love to see a study that we can then take to the C-suite and say, we have a problem here. What can we do to improve the culture? Mm-hmm.
I want to get on my hobby horse. So if anybody would like to partner with us to have us in your organization and work with you to measure culture. So culture is a difficult thing to measure because it's really no one thing. It's about 1,000 of them. But there are survey instruments that have been validated to measure security, safety culture. We might be able to adapt them for security. And we're very interested, and we have the funding right now to do that kind of work with organizations. But yeah, I think it's got a lot of promise, and it's difficult to measure, but I think it's be very good to demonstrate, scientifically that it's correlated or causal.
One of the things that we can do in looking at the software repositories is look at feature density. Like as you could almost see in a repository as you roll up to a release, are there more features? Is the rate at which features are being added, does that affect code quality and code security? So that would be something that we could look at in a repository.
I have a lot of questions, but I'm going to limit myself to two. To what extent do you make the distinction between, security bugs or CVEs versus real exploitable bugs?
Yeah, so everybody heard the question because you have a mic. So I believe, to the best of my knowledge, a vulnerability is exploitable. So a CVE has been demonstrated as an exploitable problem, and that's part of the process of becoming labeled as a CVE.
I would say that's not necessarily the case. You might have a dependency, for example, that has a CVE attached to it, but...
Oh, you're talking about in your organization. So if you're using a library, let's say, that has a published vulnerability.
For example, yes.
Yeah.
Or a security bug that's not exploitable by, say, so for example, if you have a security bug in your website, but that functionality is not necessarily, exposed.
I know what you're saying. Yeah. So that's true. And I would say, from a research standpoint, there's not the manpower and time to go through and manually verify every single vulnerability. And so what we're using are, to some degree, proxy measures, right? So the number of static analysis findings is not a perfect measure of security of code, right? But it is a measure, and it's a repeatable measure, and so it's better than nothing, is what argument.
No, I understand the challenges, but yeah.
So,
and the second question is, so most of the samples, like code samples, you use, that is Postgres, Chromium, Windows, they are developed in low-level memory unsafe languages. I was curious to what extent you take into account also like kind of programming language, types of programming languages.
Yeah, there has been research done to look at the effect of programming language on the security of the code, and they found some correlations. I would say they're not super strong. So they found generally that the conclusion the paper reached was that typed languages were stronger. But it wasn't always true my reading of the data. Yeah. So it's a bit of a mixed bag. I don't think it's a strong predictor.
Thank you very much. Very useful and great.
Thank you.
One last question. No? Okay.
So I wanted to point out that we have references. If you want a copy of the presentation, you could do that. And this is our contact information. So if you want a copy of the presentation with the references, or you want to discuss possibly participating either by offering a proprietary code repository or by offering a development team, please contact either Chris Horn or me, and we would be happy to continue the conversation. I hope you found it useful.